Pricing equations and where to start. Welcome to this video. My name is Ludwig, I'm from Phasio, and we're going to talk about 3D models and what information we can gain from them, how we can make use of that information in pricing equations. So these are really sort of the building blocks of how to get there and what to learn. So let's look at this part here, which is a cylinder, and it has sort of like a part cut out from the cylinder. So what we're going to understand from this part is what kind of information does the Phasio platform provide you based on such a part. An obvious one would be, for example, the volume. Another one would be surface area, or also clear as x, y, and z. Please note that the Phasio platform will always give you the real world x, y, and z. And you could imagine, for example, you have a part that is something like a tube like this, right? And in this tube, if you upload a model, for example, to any site or something, you might find that the x and y direction is measured like this, so that it takes the box around the part in the way that it's rotated. But what Phasio does, it's actually creating the minimal bounding box of this part, and I will put that minimum bounding box in blue. And the minimum bounding box around this part will actually go from here, somewhere like this, and we'll take the x and y and measure it from the minimum bounding box, which happens to be also the distance if you give such a part to someone in the workshop. Hey, could you tell me like how long this is? They will probably not go, put it on the desk and be like, oh, this would be like this and this. Nope, they would actually go about the x and y of the minimum bounding box. So that's how we determine x, y, and z. I'll just take this away because there's something that I spoke now about already, that is the bounding box. I'll just shorten it by b box. And in Phasio, that's the minimum bounding box surrounding the part. Now we're getting to the little more interesting ones. So a more interesting one would be, for example, the convex hull volume. And you'd be surprised how few manufacturers know this one already. So let's take a look. What is the convex hull volume? So for this part here with the cutout in the cylinder, the convex hull volume would actually be simply the cylinder. You can imagine you take this cheese, you put it into a bag, and you put the bag as tight as possible. And the body is then apparent, the volume of that body, that is the convex hull volume. And you can already tell that the convex hull volume is always at least as much as the volume. However, it's greater or equal the volume of the part. So if it's much greater than the volume, that gives you information about internal structure, which can be used later on. So let's look at the next one, a special case here in the convex hull volume. That's actually the shrink wrap volume. The shrink wrap volume is to be explained by, now we have this bag around this piece of cake, or cheese, and you suck the air out of it. You pull all the volume out of it. And now think about a cheese having holes in here, right? There's a hole, there's another hole, and maybe internal, inside the cheese, there are a couple holes as well. So when you look at the volume, these holes are not part of the cheese. So there's only X amount of volume of actual cheese, right? However, when we look at the convex hull volume, the convex hull volume takes the volume of the entire cylinder, as we talked about before. But now the shrink wrap volume sucks out the air in here, right? So these black ones, they basically bend inside here, and we take away this. They bend inside here, but they can't really quite get into the holes, right? So the shrink wrap volume is something in between the volume and the convex hull volume. So it sits sort of in between here and gives you an additional degree of information about complexity. Then that brings me already to the point of how to make use of these guys, right? So I just need a tiny bit of space here. I'll just go over there. And we'll take a sort of vertical line, and we'll talk about how can we use that, the use. So within pricing equations, we have access to this kind of information, right? Apart from like quantity and all that kind of stuff. But how are we going to use that? The first point is complexity. So I mentioned already that given the volume, the bounding box volume, convex hull volume, and shrink wrap volume, you gain information about the internal structure of a model. And that is really what I mean with complexity. You can determine whether the model is more on the complex side, having a lot of internal things that might need support, that might be intricate, that might be difficult to sort of polish or whatnot. So you can really make good use of these ratios between these sizes to gather an idea, gain an idea of how hard will it be to make this 3D model using manufacturing technologies at hand, right? A second one next to complexity might actually be that you want to estimate the number of parts that fit either in a 3D space, which could be a built volume from a MSLS machine or something like that, or MJF. And for that, you'd have your part in here. And you could determine how many times does my part fit here in 2D, and then how many layers would fit towards the Z direction. And the result is that you find the number of parts that fit in 3D. And the same you can do, of course, that's 3D. The same you can do, of course, in 2D. You can fit the part on a 2D plate and understand in all orientations how many times would that fit onto the model here, onto the build plate here. And interestingly, both of these have constraints that are geometric, while the 3D packing has, of course, also a packing density constraint because you can't print the entire volume of the chamber. But given these considerations, what you can, just from the part, what kind of information you can gain already, you can employ that, of course, inside the third column here, which then is the pricing information. So we just do 3, call this pricing, and I'll take the example of fixed cost. Fixed cost. So fixed cost can be applied in numerous different ways, right? The first way would be something like just per part, I want a fixed cost, right? So that could be something like $5 per part. So that's something totally valid to do. Another thing could be that you want the cost not only per part, but you actually want the cost to be per cut design uploaded, right? Just if you made it once, you don't want any other static cost afterwards anymore. So that would be per cut. That means it's a one-off fee in the end, just $5 one-off fee. But the more interesting ones appear when you say like, okay, I want a certain fixed cost per build volume or per build plate. And what you can do there then is you can use a seal function, because the seal function, what it does is basically something like the seal of 0.5 is 1. It's just going to round up. And even the seal of 0.4 is also 1. It's going to round up to the next integer. And there's something interesting that we can do with that, because if we put in the numerator the quantity and in the denominator the number of parts that fit in 2D or 3D, then we get the amount of builds or the amount of build plates that are required to make these parts. So you can actually charge for the amount of effort that you have to go through to make a specific quantity of parts. That's a very smart one to use. And you can, of course, also do a per complexity, so that the higher the complexity, the more you charge, right? So I just check the complexity. So given different information about the part, you can calculate lots of useful things like complexity and how many parts fit in 3D or 2D. And then you can apply that onto your fixed cost, but also on variable costs like volume costs or whatever. So there are plenty of opportunities to explore different building blocks here. And within the documentation, we will go in depth on different manufacturing examples so you can understand how to price your parts well within Phasio. Thank you for watching, and please feel free to reach out if you have any questions.